Alrighty, so it's getting dark in here, and I also have a cat who is at the moment sleeping on my lap, but she might get hungry. If you see in like an orange tail go across the screen here, just roll with it. In this lesson, we're going to introduce quadratic functions, some of their key features, and lay a foundation for us to build on. Sometimes I have called this a mini unit, meaning it is very, very short. And so you can expect to have a test or quiz fairly quickly on the tail end of this, although I had to make some adjustments because of some changed plans. So we want to start with what makes a function quadratic. Now, the technical definition of a quadratic is what I call clunky. I put it in there in quotation marks. It gets kind of tangled up in other vocabulary. So we could say it is a polynomial of degree 2. But then that raises the question, what is a polynomial? Well, a polynomial is an expression, and we start going down this rabbit hole of like definitions, and really we don't need to do that. So what I'm going to go with here is an informal definition that I think will be workable for where we are right now. And that is, we can create a quadratic function if we take a linear function and we simply add an x squared term to it. Okay, so if we know what a linear function is, we can recognize equations of lines. And what we're just going to simply add into that is an x squared and nothing more than an x squared. So we're not going to throw in an x to the third or x to the fourth or square root of x or anything like that. Okay, we just add in an x squared term. So I have some examples here. So you have the linear function 2x plus 4. And maybe we would add into that 3x squared. Okay, and that would take our linear function and make it a quadratic. Now we could always also subtract an x squared, because subtracting is really just adding a negative. So in other words, you could have a negative number in front of your x squared. So we could maybe just subtract, we'll just call it like a regular x squared. And then this last one, I made the linear one a little bit different. So it's just like h of x equals 1/2 x. Okay, and that would be like 1/2 x plus 0. And we could put in, I don't know, we could put in a half x squared. Okay, so a couple things well, that was interesting. I want you to note about that is that your x squared term can have a coefficient. The coefficient can be negative, the coefficient could be a fraction, it could be a decimal, but we're not adding more stuff into that. Okay, we're not adding x to the thirds, x to the fourths, we're not square rooting it. We also don't have to have all of the pieces of the linear function. So we could have just the x term, we could have just the constant term. So we could do like 5 plus x squared or 5 minus x squared, or we could just have like 0 and just put in an x squared. Okay, so that's how we can build a quadratic. The key thing you want to look for when you're determining if something is quadratic is the x squared, though. If there is no x squared, it is not a quadratic. All right, that's the focal point of this. Now we typically write them in standard form, meaning we put the x squared on the left, the x in the middle, and the constant in the right. So this way of writing it would be like a little bit weird. We might write it as this instead. We'd put the 3x squared on the left, and then we'd put the plus 2x in the middle, and then the constant on the end. Okay, so the g of x, okay, that would be written as negative x squared, because again, we're subtracting it. That's the same as adding a negative. So the negative is attached to the x squared, minus 3x plus 5. And then this last one, h of x, we could write that is as 1/2 x squared plus 1/2 x. Okay, and if you wanted to, you could say plus 0, but we usually don't. All right, so that's what's called standard form. There's nothing about the definition of a quadratic that says it has to be in standard form. And there's 3 main different forms that we have. So like with lines, we have like slope intercept and point slope in standard form. In quadratics, we have standard form, vertex form, and factored form. are the main forms that we'll write it in. But if you've got the different terms listed out as a sum or difference, we would typically write it in standard form. So the x squared on the left, the x in the middle, and the constant on the end. If you don't see one of these, you can assume it is 0. Okay, so if you don't see an x term, you would assume it's 0x. But if you don't have an x squared term, then you don't have a quadratic. Okay, so you got to have that x squared term. So what's the most basic quadratic we can have? And I'm a little nervous going through this PowerPoint. I am noticing that my keyboard on my laptop, some of the keys are getting very, very hard to type with, and I'm not catching all of the typos from it. So that's just becoming a little bit more frequent. So if there's a typo in here, I'm just going to apologize in advance. I'm really sorry. So what's the most basic quadratic that we could have? Well, that is f of x equals x squared. Now, technically, this is f of x is 1x squared. Okay, so the coefficient in front of the x squared would be a 1 plus 0x plus 0. But we don't normally write the zeros because it's extra. Now, there are times when we want to know that it is a 0. Okay, when we get to some of our higher order polynomial stuff, we want to recognize that when we're not seeing the terms there, it's because we have a coefficient of 0. But we don't typically write them. So that's as basic as it can get. It's we would be working with a horizontal line on the x-axis, and then we add the x squared to it. It's got the x squared, which is essential for it being a quadratic, but it doesn't have anything else from the linear piece to muddy it up. Now, we're going to graph this two ways. We're going to graph it by making a table, because I really want to emphasize that that's where our graphs come from. They come from picking values and then finding the mapping, okay, and then plotting the points from the mapping. But in terms of efficiency, it's not very efficient way to graph. So we're really only going to do it this one time and then select it other times when we might be looking for some key points. So here we have the function f of x is equal to x squared. Now, if you're wondering why is it capitalized and why is it lowercase, the PowerPoint automatically capitalizes all of them, and it just gets to be a lot to keep going back and fixing it. So I just found like I am taking a lot of time to go back and just change it. So if it really bothers you, I'm sorry. Let me know if it really bothers you. And if it is the year that I'm making the videos, I will make sure that my future videos, like I go back and fix it. Now, we can pick anything we want for the x values. So what I think I will do when I present this in class is I'm going to give you a couple of values to start with. Okay, and we want to try to keep them small. But then what I might do is open it up for the class to pick like a final value. That's supposed to be a question mark down there. Question mark. Maybe a question mark. Get the right color. There we go. Okay, to pick one, it kind of looks like a 7. It's intended to be a question mark. Just so you guys can see that really you can pick anything you want. So what we're going to do is take our f of x is equal to x squared, and then we plug in the value for x. So this is -2 squared. Now remember that to square something means to multiply it by itself. So f of -2 is 4. And if you recall, that's showing us our mapping. Okay, it's showing in this particular, that's a 4. There we go. In this particular relationship, that's what it maps to. So -2 would map to a 4. Let me see if I can do this a little bit. So we've got -2, -1, 0. Sorry, you guys are never going to want to watch a video again. Well, you don't want to watch any videos anyway. Who am I kidding? You're doing this because you need to. -2, -1, 0, 1, 2. And so we've got the 4. Okay. And so we've got that mapping. -1, that would be -1 times -1, which is 1. And so we've got this piece, so it's mapping there. 0, love 0. 0 times 0 is 0. And so we've got the 0 mapping to the 0. And now here's where it starts to get a little bit more interesting. Now we have a 1 squared. So 1 times 1 is 1. And you end up with that like doubling up on the mapping. So this is not what's called a one-to-one function. Lines are one-to-one functions. Quadratics are not one-to-one. And then 2 squared is a 4. And so we get that doubling up on the 4. And then you can pick a point. So let's say, well, let's go and graph these ones. Whoops, man, my touch screen is not really behaving either. So we have the point -2, 4, which is right there. We have the point -1, 1, which is there. 0, 0, 1, 1, and 2, 4. So you can see it basically looks like it's like curving like that. And then you could pick another point. So I've got this set so we can go out to like +5 or -5. So we could just say for funsies, like, oh, well, let's pick a 4. Okay. And then 4 squared is 16, which is going to land us here. All right. And you can see that, yep, that like looks about right. Okay. And it would do the same thing on this side. And so you get what this basic shape is. And you could play around with this some more. You could say like -5 should take us to 25, which I don't have it quite like steep enough. It should be more like that, but it's enough for you to get the idea of what the shape is. You can also see that this is very, very inefficient. You would not want to graph these this way all the time, and there are some shortcuts for graphing them by hand, as well as, of course, we have our graphing technology. All right, so some of the vocab, and I am not one for just like throwing formulas at you, but I don't like for figuring out the derivation of this. I think I do have a video on my other YouTube channel, not this one, but the math help, the like kind of general one, my like and subscribe channel, where I go through like where some of these formulas come from. But all right, so the shape name. The name for this shape is called a parabola, and I might have said that on the previous slide just out of habit. Now, I have had students call this a parabola, and they put the emphasis on the bowl, like the word bowl, to remind themselves of the shape that a parabola looks like a bowl. It's rounded on the bottom. But the way you do say that is parabola with the accent on the ra. Now, the axis of symmetry is the vertical line down the middle of the parabola. So the parabola is symmetrical on either side. And so the axis of symmetry is the vertical line over which the parabola makes this mirror image. It is not a part of the parabola, which is why it is in a dashed line. So we'll often try to do that with a dashed line, but it is a feature of the parabola. It is useful, especially if you want to use the symmetry. If you have a point on one side, you know there has to be a symmetrical point on the other side. And so you could actually like count to see like how far over it needs to be. The formula for the axis of symmetry is the opposite of b over 2a when the parabola is in standard form. Okay, and this should be familiar from Algebra 1. So I feel fairly comfortable doing this quickly and assuming some background knowledge. So when you have a quadratic, you have like the ax squared plus bx plus c. A is the coefficient of the x squared, b is the coefficient of the x, and c is the constant. So if you pull those numbers out, then you should be able to find the axis of symmetry. Now, the b value here, you'll notice when I said it, I said the opposite of b. I did not say negative b or minus b. It's not wrong to say negative b or minus b, but way back in the day when I was a freshman in high school, I had a math teacher, Mr. Oakes. Mr. Oakes, when he said these formulas, he always said them out loud, the opposite of. And that was a reminder that it's not necessarily a negative number you have there. It's the opposite of whatever your B value is. And then we have the vertex, and the vertex is like the turnaround point. You'll also hear it called a minimum or maximum value, depending on whether it's at the bottom or the top of the parabola. And that would be like that point right there. It is on the axis of symmetry. So the highest or lowest point on the parabola, the maximum minimum, called the vertex, is on the axis of symmetry. And then this is, I'm glad I gave you guys the disclaimer. That should be the word plug. Plug the axis of symmetry into the function to find the y value. So the axis of symmetry formula is going to give you an x value, and then you can plug the x value into the formula, the function, and get the y value, and that will get you the coordinates there. We're going to practice that in a little bit. All right, on the next slide, we have the Desmos version of that. So you can plug in f of x equals x squared, and Desmos will have the function show up. And you should probably be able to see it. So here's the point 1, 1 right here. Here's 2, 4. Okay. And I think we should be able to see 3, 9. So 3 and 3 is over here, because that's scaled by halves. And then, yep, up here is the 9. And then here's the -1, 1, the -2, 4, and the -3, 9. And we could, of course, look further up. The vertex is at the point 0, 0. And that's where it's the turnaround point. We're going to talk a little bit more about that in a few minutes. All right, so we're going to use Desmos to practice the calculations. So over here on the left, you can see the function. The function is -2x squared plus 4x plus 3. And I've got the vertex already highlighted, okay? And so you guys can see where the axis of symmetry is. The axis of symmetry is that vertical line right there. Okay, I'm doing it dashed. And you can see that we do have symmetrical points. Okay, so we have a point over here, and then we have the mirror point over here on the x-axis. And you could literally count, like it is 1, 2, 3 blocks from that point to the axis of symmetry, and 1, 2, 3 blocks again from that point to the axis of symmetry. Now, here's where we use the formula. So if we're asked to find the axis of symmetry, we know the formula is the opposite of b over 2a. Now, coming over here, a is equal to -2, b is equal to 4, and c is equal to 3. So the opposite of b is, well, in this case, b is 4. So the opposite of 4 is -4 over 2 times a, which is -2. 2 times -2 is -4, and anything divided by itself is 1. And I want you to notice that that 1 is that one right there. It shows you where the axis of symmetry is. It's on the line, vertical line, x is equal to 1. Now, how can we find that 5? We take that 1 and we're going to go ahead and plug it into the formula. You know, it would be awesome is if I wrote what I meant to write. Yeah, so we have -2x squared plus 4x plus 3, and we're going to go ahead and plug in the 1. So we have -2 times 1 squared plus 4 times 1 plus 3. 1 is a nice friendly number there. 1 squared is just 1, so that is -2 times 1. 4 times 1 is just 4, and then we have the plus 3. -2 plus 4 is 2, and 2 plus 3 is 5. And there's your x and there's your y, okay? It tells you the mapping, that 1 maps to 5, and that is the vertex. So that's how you find the calculations by hand. How much work do you need to show in the calculations? Here is what I would want to see. So I can be really clear. I'm going to turn the highlighter on and I'm going to show you like what I want to see. I would want to see this line right here. Okay. So I'd want to see Not necessarily you got to copy the formula, but you've got to show me what like the setup of the formula. So you don't just go to x equals 1. Now for the other calculation, I would want to see this line right here. Okay, so I'd want to see that once you had the one, you knew what to do with it. From there, I am okay if you jump to the answer, because you can use Desmos to get the answer. You can use calculator. You might be able to do it in your head if it's really simple. But for work that you are required to show, like to get full credit on something that I'm looking at, like on your homework, that is what I would want to see. So it's not too much like written work, and then you can always use Desmos to check it. Okay, so you can use set it up, find the answers, and then graph it. And I did make sure on your homework assignment that all of the numbers like check. You should be able to see them. All right, so now we're going to introduce a new feature, okay? A new feature of quadratics. Now, lines have the same slope everywhere. That's actually what makes a line a line. They're always heading up or they're always heading down unless they are horizontal, okay? In which case they're flat. But for the most part, like they're all they never change, I guess is the key thing there. They always have the same steepness. So they're always heading up or they're always heading down, and it doesn't matter where you measure the steepness or the slope, it's got the same slope. But parabolas do not behave the same way. Quadratics curve, so the steepness changes and so does the direction. So for example, like here it's very steep, but here it's not as steep. Here it actually looks like it's flat for a second. And now the steepness is actually going in the other direction, and it will get steeper and steeper and steeper. So for the first time, we're dealing with something that has this curve. Now that introduces some new vocabulary. They're going to head up and then turn around and head down. That would be like this kind of parabola, or they're heading down and then they turn around and head up. And where that changes direction, that maximum or minimum point, determines when it goes from being increasing to decreasing or vice versa. That's our new vocab. Increasing simply means that the function goes up from left to right. So looking at this, this would be increasing because as I'm moving my finger or pen from left to right, the graph is going up. On this one, this is increasing here because it's going up. Decreasing simply means that it goes down from left to right. So this would be decreasing because it's heading down. Don't let that arrow throw you off. So I think that can tend to throw students off because there's an arrow pointing up. But when we're tracing the function, we're always going from left to right. That arrow just means that the graph does keep, like there's more to the graph there. Okay, but as we're tracing it from left to right and it's going down. And then on this one, this would be decreasing. Please, please, please do not try to memorize a pattern here. So every year I have students that are like, okay, if the parabola is like this, then decreasing is on the left and increasing is on the right. And if it's like this, then decreasing is on the right and increasing. Don't do that, okay? I understand that there's a temptation to. What I want you to work on is learning the definition. Increasing is heading up as you go from left to right. Decreasing is heading down as you go from left to right. And the reason I want you to focus on that is because eventually you're going to have stuff that does that, okay? Where it's kind of going up and then down and then up and then down and up and then down. And then like the pattern that you're memorizing doesn't hold true anymore. Like you don't have this, if it's shaped this way, it's on the left and right. Now you've got to go back to, is it heading up or is it heading down? Okay, so just keep that in mind. All right, so this is like what I intend for you to do on your homework. So we're going to highlight the increasing interval in green and the decreasing interval in yellow. So on the first one, as I am tracing it, so I go to the far left, okay, as far left as I can go, and I'm going to start moving to the right. And really get that locked in your head, like this is a left to right motion. I am decreasing, 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 decreasing. And then right here at the vertex, now I am increasing. I'm going up, increasing, increasing, increasing. So it's asking for the increasing interval to be in yellow. So I'm going to go ahead and, I want that to be a highlighter. There we go. but then it changed the color. So we can do this. There we go. Okay, increasing is in yellow and decreasing is in green. Okay, now that's messy. So when you do it, try to like be a little bit neater about it. Okay, next one, highlight the increasing interval in green. I did that backwards. Increasing interval in green. There we go. And the decreasing interval in yellow. My apologies. All right. Colors are so hard sometimes. Actually, I'm just probably really tired. It's been a long day. So increasing interval in green. Okay. So increasing interval in green, I'm heading up. Okay. And again, move your finger, cursor, whatever, to the far left, as far left as you can go, and then trace to the right and figure out what am I doing. So I'm going up, increasing, increasing, and then right here at the maximum or the vertex, decreasing, decreasing, decreasing. So that will be in yellow. Nothing is cooperating with me. Like the touchpad, whenever I'm changing the tool, it's like it's messing with the color. So anyway, all right, last one. The vertex is like way over here. This is like a gradual one. So just trying to get you comfortable seeing different kinds of parabolas. So we want the increasing interval in green. So that would be, and like again, it did not change the color. I am so sorry, guys. I really am. Okay, I think I have it. Increasing is green and decreasing is yellow. And again, always move your cursor to the left and as far left as you can go, and then just trace the function. I am heading down, therefore that is decreasing. And right when I get here, now I am heading up, which makes it increasing. All right, so last but not least, you have some practice problems. For number one, it's a multiple select. So which of the following are quadratic functions? So just look at them and say, oh, A, B, and C are quadratics, or whatever your answer choice is. For numbers 2 through 5, find the axis of symmetry in the vertex using the formulas. We did that in this lesson. And then graph them on Desmos to check your work. But you should know what you need to show. For 6 and 7, what I did was I took all the numbers and tick marks off of there just so you could see the bare bones of it, and copy something that looks like this. All right. And for 6, highlight where it is increasing, and for 7, highlight where it is decreasing. If you want to do those on the same graph and do it in different colors, that's fine, but you need to indicate which one is which. And then for 8 and 9, you're going to do the same thing, highlighting where it is increasing, where it's decreasing. And then for 10, it's a little bit behind my face there. How is a function being positive different from it being increasing? So positive, we talked about when we did our Desmos lesson for lines. So you might want to look that up. You feel free to AI that, Google it, come up with an answer. Just make sure that the answer that you're writing down makes sense to you, but you are free to look that up. So I know this was a little bit longer lesson. Hopefully it was okay. It was also really unpolished, and I do apologize for that, but at least my cat behaved. So I hope this helps. You guys know how to find me if you have questions.